My name is Jonas and I welcome you to this video where we will look at best practices for implementing the control system in EEROS using a motor and encoder as an example. Before we can start with the actual implementation, we need to know how we want to implement our control system. To do this, we need to derive the control system theoretically and sketch it on paper as a system of blocks, signals, and time domains. In doing so, we should think about the following questions. Which blocks do we need? How do we arrange them? Which ones should we group in a subsystem? What periodicity should the blocks run at? EEROS provides us with many blocks and most of the time we do not need additional ones, so please make use of them. However, we can also create our own custom blocks if we need one that is not available. But back to our example with the motor and encoder. If we want to read the position of the encoder, then we need an encoder block as an input. And if we want to set the motor voltage, then we also need a motor block as an output. These two blocks are available in EEROS under the names peripheral input and peripheral output and can be accessed through the hardware abstraction layer, which we covered in another video. Finally, to control the motor, we need a controller that receives the position from the encoder and sets the voltage of the motor. To keep this video short, we won't go into control theory and simply draw the controller as a subsystem. Of course, we would need to define the subsystem if we were to implement it. Now that we have our blocks and signals, we just need to define the time domain in which these blocks run. It makes sense to let them all run in the same time domain, which we can set to 1 millisecond in this example. Once we know what our control system should look like, we can start implementing it. The EEROS template project provides us with a basic structure for the control system, which we can leverage to implement our own. First, we should start in the control system header file and include the header files for the blocks that we want to use in our control system. After that, we should define the blocks, subsystems, and time domains. And that is already everything that we have to do in the control system header file. Some blocks must be initialized in the control system source file. For example, we assign the encoder with the name enc1 in the hardware configuration file to the peripheral input. Further, we also have to initialize our time domain here. Next, we should name our blocks and signals. This will help us later when something is not working properly and we need to debug our code. After that, we can connect our blocks and subsystems according to our control system previously sketched on paper. For example, we connect the input of the controller subsystem to the output of the encoder block. Last but not least, we add all of our blocks to our time domain in the order in which they are to be executed. And finally, add the time domain to the executor, which ensures that it is executed with the specified periodicity. It is a good practice to regularly test small parts of the control system during implementation. For example, first we could define only the encoder and test if the read position is correct. Next, we could define and test the motor, and so on. We have already talked about the possibility of creating our own custom blocks and subsystems. But how can we do this? In the EEROS template project under Inc. Custom Blocks, Custom Block Template.hpp, we find a template that we can use to create our own custom block or subsystem. To do this, we make a copy of this file and rename the file, the include guard, the class, and the constructor. The implementation processes for the custom block and subsystem are very similar. Actually, a subsystem is almost the same as a custom block. First, we will look at the custom block and then talk about the differences. To implement the custom block, we should first derive the formulas we want to use in theory. Once we know what inputs and outputs we need and how to calculate the output values from the input values, we can start with specifying the number of inputs and outputs of our block. If we want to create a block with 0 inputs and outputs, then we should inherit from block instead of block IO. After that, we define the intermediate variables and initialize them in the constructor. Finally, we implement the run method, in which we calculate the output values from the input values according to the derived formulas and set the timestamps accordingly. If we consider our example with the motor and the encoder from before, we could implement the controller as a custom block. The simplest controller imaginable uses only a proportional gain Kp. The control law is the gain Kp times the difference between the position setpoint and the actual position. To implement this, we need a custom block with one input and one output. We also need to define variables for our position setpoint, the gain Kp and the output voltage U, and initialize them in the constructor. After that, we can implement the run method, where we calculate the output voltage U according to our previously derived control law and set the output signal and timestamp. To change the setpoint, we have also implemented a setter function. We could do exactly the same thing by using a subsystem instead of a custom block. To do this, we need to rewrite our control law into block form. We first create a constant block for our setpoint and calculate the difference between the setpoint and the actual position with a sum block. Then we multiply the difference by the gain Kp using a gain block and get the voltage. In the code it looks like this. At the top we include the header files for the input, the constant, the sum and the gain. We need the special input called input sub because we want to be able to connect this input to the sum block later. Since we define our own inputs and outputs, we inherit from block and not from block I/O as we did before. This is also the main difference between a subsystem and a custom block, apart from the fact that we use blocks and not formulas inside the subsystem. Next, we define all the necessary blocks under the protected section and initialize them in the constructor. After that, we connect the blocks according to our outlined subsystem. Hence, we connect the setpoint and the actual position to the sum block, negate the second input to get the difference, and connect the sum to the gain Kp. In the run method of the subsystem, we can now simply call the run methods of our subblocks in the order in which they are to be executed. We also need to slightly adjust the setter function for the setpoint so that it now sets the value of the constant block. Finally, we need to implement getter functions for the input and the output of our subsystem. The input is our previously defined input sub, and the output is the output of the gain Kp. The functionality of this subsystem and the custom block we created earlier is now the same. Thank you for following me through this implementation guideline, and I will see you in the next one.